And related to this point, another question we had is that essentially what we were discussing today is almost linear, right? It's all linear. But the impedance can be also, I mean, it's defined at the level of stiffness damping, and that's it. But we could also include some higher order or terms or components that, as far as I know, it's a little studied yet. And our question was, it is worth studying these higher order components in humans or in robots? I mean, they could add something to the agility of our robots.
Yeah, I would argue that's very important. So one of the human neuromotor system is highly nonlinear, right? And we tend to study it using these small perturbations, and over that range, these linear models work quite well. But one of the ways that some of the nonlinear actions become really important is when you start to look over larger excursions, more functional motions. And just one example is if you look at locomotion and you look at the Achilles tendon, or any tendon, but the Achilles is really quite dramatic. It has a very highly nonlinear stress strain relationship, so that as you stretch it, it becomes much, much stiffer, which gives you kind of intrinsic stability simply as you're creating forces. And that the tendon itself tends to actually dominate the mechanical response of the ankle much more than the muscles do. Even though, as I think was Neville's talk pointed out, the importance of cross bridges and generally muscle activation increases stiffness. But it's always in this series system where you have a tendon connected to a muscle, it's always the most compliant element that dominates what you see. And so the very nonlinear properties you see of torque stiffness characteristics at the ankle are actually come into play with the tendon. So it's kind of increases stability of the ankle just as you generate more force. So it's just one of many examples, I think, where the nonlinearities are very important. The linear models work well over smaller ranges, and they're good for understanding what's going on, but you need to look over multiple ranges to understand the importance of those nonlinearities.
Just to add an example, I think the fingers also have a very nonlinear stiffness characteristic, and also hysteresis are there. And I heard, it's not of my work, but I heard that when you design an extra gloves, or like the some like mechanical gloves that would assist you to let's say make the like stroke patients to enabling the grasping again, and that designing your gloves like appropriately requires to understand the stiffness characteristic of your fingers, because if you don't like if you like ignore the specific profile of the finger stiffness, then the glove would not work as you desired. So in terms of the even for the application side, when you design or build the robots or the devices, understanding the nonlinear characteristic of impedances is, I think, is very important. And also, as Professor Eric Pearl mentioned, especially for like functional like tasks like walking or running, for those tasks like when you have like a large movement overall, then I think the nonlinear characteristics should be like highly regarded. Just a perspective.
Mm-hmm.
So from a control point of view, I would argue that taking into account the nonlinear dynamics of the system is very important. But in terms of implement, if you think of I'm going to write down a control law that basically realizes a mechanical impedance, at least in abstract, I think a piecewise linear is sufficient to look at it in terms of stiffness and damping, because if it's varying over time, you will be able to capture whatever nonlinear characteristic they care about, and at least it's computationally tractable, so you can do something with it. That's usually what you do when you do differential dynamic programming, right? You solve a nonlinear optimal control problem, but you basically do piecewise linear approximations, and it gives you linear feedback. But since it's varying over time, you can approximate pretty much anything that you want, right? But really, what I would say that really what matters is the nonlinear dynamics that you need to take into account. The other thing that I was wondering, I think it was part of your question, Giuseppe, is whether or not we need to take higher order terms, right? So like inertia shaping and higher. And so I don't know, but my question is that isn't it sufficient to do force feedback there? And you can just ignore everything else after that. Because inertia shaping is equivalent to basically having a force feedback, isn't it? So maybe that's enough, but I don't know. That's more a question. I don't really know if this is the right way of thinking.
No more comments on that point?
Well, one more comment. I don't know how much it's relevant to robotics, but if you look at the design of vehicle suspensions, that's essentially designing an impedance, then you never stay as simple as second order. You always go much higher than that because of the fact that you can get dynamic absorption effects that match the spectral characteristics of the surface you're moving on. Does that matter for robots? I can't tell, but there certainly is a context.
But do you think in terms of robotic implementation, doing force feedback explicit would be sufficient, or do you think we need to explicitly really model the higher the basically the higher order derivatives of the positions there?
So again, I don't have direct experience, but for example, as some work by a colleague or colleagues working on robotic locomotion with the mini cheetah, to conserve energy, they're adding essentially a pendular dynamic vibration absorber. So something that allows the payload to move antiphase with the robot body, that dramatically reduces energy consumption. So that's not just pure force control with high bandwidth feedback. I think, as with most problems in engineering, it depends upon the problem you're trying to solve.
Yeah, so like commenting on like Neville's example, like the auto vehicles, like the suspension systems, I think for that, like it was really, how do you say, like the system was easy to be like linearized, like because you wanna how do you say, like the whole body like can be like reasonably approximated by like just like a single like m block of the mass, and then adding like stiffness and damping, a linear stiffness and damping under the block of the mass would like would be enough to like execute the task, like suspending provide some suspension maybe. But for like because the lagged system has been mentioned for walking or like running, where, and actually if we think about like impedance in terms of walking and running, I think one biggest question that I can raise is which impedance are we talking about? So like Professor Antonio Bicchi said that what are the right things to do is a very important question. And for like running or walking systems, so let's say we can say impedance in terms of like springs, F equals Kx, but what is the X here? Like, is it the spring between like foot and the center of mass, or would it be like joint stiffnesses? Like, which impedances should we look at is also another like biggest question that that is a biggest and challenging question and critical question. When we are like reaching experiment, we do know exactly what the task is, but for walking or running, the task itself is quite unclear, and defining which impedance we should investigate is also very challenging. So I was wondering whether like those who worked on like locomotion and impedance have any like perspective or like some comments that you can like throw out.
Yeah, so in a way, like a mathematical model, like it is an abstraction, and the level of abstraction we use depends on what the question we aim to answer. So if we consider kind of like the motion of the center of mass, then, well, considering a spring between the center of mass and the leg, and between the center of mass and the foot, an abstraction of the leg is one way to model locomotion. If we care about, well, how the center of mass moves, then that might be enough. If we care about what the muscle activations are, then probably we should model the entire leg, the kinematics of the leg. But let me kind of, I would like to come back to the question. So there was a general question of when would impedance matter? When would an actuator, a variable impedance actuator matters? And there is a general consensus that when we have interaction with an environment, then, well, having a variable impedance is important. So one way to somehow take into account environmental uncertainty, another way to somehow kind of control the system. But there is another class of tasks also that appears to be very suitable, well, kind of like variable impedance actuators are very suitable for. And these are tasks which are related to energy accumulation. So imagine that we have a small actuator. So we want to avoid using a large actuator on a robot. So we have a small actuator which is force limited or torque limited. But we aim to achieve, well, we aim to accumulate a large amount of energy, for example, to run fast or to jump higher. So then one route, one way to use these kind of actuators is to do resonant forcing. So through time, we are using a very small, very weak actuator, but through time, we achieve energy accumulation. We achieve something that would require a much larger actuator, an actuator that can provide much more force. So this is one option, one kind of class of task. So energy accumulation is not a task of force. Same way as interaction with an environment is not a task, but it is present, it could be present in many tasks if we use it.
So to add to that, in locomotion, I guess it really depends on many things, right? So my experience is that the center of mass, you usually want this to not be compliant, because if it's compliant, you're falling pretty much, right? If you get pushed, your center of mass needs to not move. If it moves, your center of pressure goes out of your foot and well, it gets on the border, and then you start falling, right? At the same time, your leg needs to be rather compliant, the swing leg, before you make contact. And the moment you've made contact, you want to stiffen up to some extent, right? So this you can capture if you model the full dynamics of the robot. You can capture those different things separately by modeling what kind of uncertainty matters, would have an effect on stability and things like that. So I guess you need to be able to have different tasks with different types of impedance, and usually we tune those things differently, right? Another thing we have not talked so much, we talked quite a bit about compliance, and I think compliance, it really depends, right? For the swing leg, it's important when you're on the ground and you need to support your center of mass. Compliance is not, you maybe don't want so much of it. Damping is very important. We've realized that if you want to dynamic things and you have impact, you need damping. You need to damp as much as you can, right? When you hit the ground, pretty much. And how do you automatically compute the proper damping profiles that you actually need, right? Because you don't necessarily want to have damping when you start to jump. At least you want damping that goes the other way around. So you need to pump as much energy as you can in your system, right? The moment you hit the ground, you want the opposite. You want to basically be able to dissipate as much as you can. The stiffness part of it is not so important anymore. At least from what we see in the jumping robot, right? The damping is really going to make it, is a big deal of that. How do you compute that? It's not so clear. So we propose a thing I showed in my talks, that we have a way to think about that, but it's maybe, yeah, I think there's a lot of work there. How you find those things.
Sorry if I may ask. So if you set the center of mass as stiff and not compliant while moving, if there is an obstacle and you touch it with your body without realizing it, in that case, the interaction force may destabilize the robot, or not.
Yeah, but that's what I'm saying. So if you're taking a step, right, your center of mass. So basically, the relationship, the center of mass defines where. So if you're on one leg, if you take a simplified model, the center of mass motion will define where the center of pressure is doing, right, and vice versa. So if your center of mass, you have a big excursion of your center of mass, the moment your center of pressure is on the edge of your foot, you're falling, and then that's it, right? And you're not doing anything about it. So, but having a stiff center of mass doesn't mean that the rest of your body is not compliant. When you take your swing leg is moving and hits an obstacle, if it's compliant and have sufficient damping, it's going to absorb the shock, and center of mass is not going to see it. So that's what I'm saying. We're very redundant, right? So different variables that you care about should have different relationship into how much they can deal with disturbances. So one doesn't preclude the other, right? I can be compliant when I hit the obstacle and make sure that my center of mass doesn't move at the same time. Or it moves in a smart way, right?
What meant is that you may interact with the environment, not just with your limbs, but also with your body. In that case, you should be compliant also with your body, right?
Yeah, but it doesn't. That's what I'm arguing, right? That your body can be compliant while your center of mass.
Okay, I see.
So much, right? Yeah.
Okay.
I agree. I mean, it reminds me of like balancing, or if you're riding on the train, right? You want to keep your legs compliant to reject those disturbances, but keep your center of mass, like you said, like right within your base of support, so you're not falling. So I agree. How then do we go about implementing that or learning what is the right? Now you start to think about, if you're setting compliances at the joint level, right, instead of these smaller, or instead of a simplified model, how do we learn those for given tasks, right? So now you have a bunch of these subtasks that have to work together in order to create a desired whole body behavior. Thoughts? I mean, I don't expect an answer, but I see that as being the challenge, right?
I'd love to tack on a question to that rather than an answer. If we're assuming that the implementing control into robots should be modeled after humans in the way that they balance on a train, for example, is that really the best model? Or are we assuming that over evolution we've been able to achieve impedance control in an idyllic way for our own bodies? And will that be idyllic for robots, or is that a naive assumption?
I think the overall goal is the same, right? Ultimately, if you wanted to match that's the question of how do you get there, and does it have to be human inspired? No, I think at this point, if it works on a robot, great, right? But the challenge, I guess, we look to humans because they can do it, and so if we can gain at least some insight, I think that's at least what I've seen in terms of like human inspired or bio inspired robots. It's moved from from biomimicry more to what are the general principles that we can extract to give us some clues as to how we could do this in robotic systems. At least that's, obviously, feel free to comment on that, agree or disagree.
I'd like to make a comment, because look at the analogy with flight. So we have flying machines that far outperform biological birds and bats. On the other hand, if you look at agility and perching, you never see in a 747 perch, have you? So I think that they're just different, the different design spaces.
Yeah, I'd say one of the simplistic answers, from someone who's not a roboticist is, when you think of the human body, rarely do we have a single task, right? So if I'm walking, my primary goal is not to fall over, but my secondary goal is to get where I'm going. And you can argue which is primary, which is secondary. If you're playing soccer, you have the goal of staying upright, but then you have the goal of being compliant as you catch a ball, and then stiff as you launch it down the field. So to think of a single task or a single criteria for optimization, I think is a little too simplistic, and we need to think of the whole. What are the entire goals of the body for any given activity we're participating in?
I have two quick points. One kind of about the discussion previously about kind of energy dissipation and the discussion of damping, one kind of point to add to that is with impedance control, we also have the ability to adjust the rest length of the elastic element. And that's another mechanism that's used to dissipate energy. And I think we should remember that in addition to damping. So we can dissipate energy by losing it over damper, but also by changing the rest length to do kind of negative mechanical work. And then the other point I'd like to make is a potential experiment that I think would highlight some of these challenges. Kind of what is the role of impedance control in locomotion, or in locomotion of assistive technology? And I'm sort of imagining an experiment that contrasts controllers that are developed with position control, which would be a high impedance controller, and then a controller developed with follows kinetics, so a torque controller, and then comparison with an impedance controller that's kind of a trade-off between those. And looking at sort of functional outcomes, it says if you have stiff impedance, you get this sort of behavior, low impedance, you get this behavior, and then looking at how people respond to disturbances potentially. I think that might be kind of a concise experiment that tries to get at the value added by kind of a biologically inspired impedance controller.
So let me add to the comment on damping. So we have now two options. One is to use damping, another is to change the rest length. There is a third option to damp on variable stiffness actuators. These are great actuators. Like the third option is to reduce stiffness when a spring stores energy. So when the spring stores energy, if you reduce stiffness, you lose energy. So there's a third way to damp. But maybe kind of like in jumping, for example, if of course, if the task is to jump higher, then throwing away energy might not be the goal. Maybe storing it, like damping could be understood as not only throwing away energy, but maybe kind of opposing the movement with the force. And a spring can do that kind of like in every task. So storing away energy and then well, reusing it to jump higher would be also an option. So three ways to damp in like nutshell, three ways to damp on variable stiffness actuators, at least three.
If I may ask a quick question too, I think it's both Dr. Rouse and Professor Hogan. I know you spend a lot of time estimating human ankle stiffness during walking. And we've already brought up the topic about it's going to be hard to estimate, say, knee stiffness because you can't really isolate perturbations to the knee. So what are your opinions about numerically estimating those stiffnesses or damping parameters? There's a lot of learning approaches out there, or a trajectory optimization based approaches. So what are your opinions about that?
Go for it, Elliot.
Okay. So my thought would be, like, right now we have a mechanism we're developing that applies perturbations to the knee with an exoskeleton, and I'm confident that we can perform estimates of knee mechanical impedance during locomotion with this system, and I'm very excited about that. We've also been kind of at the same time talking with Massimo Sartori about doing a kind of a paper where we do a direct comparison between kind of an EMG-based method using musculoskeletal modeling and a direct empirical measurement provided by our group. And I think that will shed some light on the kind of appropriateness of modeling impedance without using an empirical kind of perturbation approach. And if it turns out that those models provide high quality or accurate estimates of impedance, that would be a really good thing, I think, for the field, because these empirical studies are quite challenging. And it would be really wonderful to maybe have a parallel path to answer some of these questions.
So I'd like to mention, so I'm not sure if it's relevant, but Megan can describe some of the work that she's done, in which she's shown that humans can actually estimate limb impedance just from visual information, which is technically should be impossible, but in fact humans can do it. Megan, you want to explain?
Sure. Yeah. So I mean, you can think about it when you. I guess we're not in the clubs nowadays, but you look at somebody and you can tell, for example, are they a good dancer? Are they not? Right? Or we can tell a lot of information by looking at just motion, even just people's mood. or how they're feeling. And when you think about what is it that we're actually okay, there's a lot of psychology experiments showing that we can perceive these things, but what is it mechanically that they're actually perceiving? And it turns out that we ran some experiments where we literally just showed people two lines moving on a screen, just two links with no other information, and asked them to rate the stiffness of this arm. So it didn't know anything about the mass properties, the underlying controller, didn't even know what plane it was operating in. And yet we see these really nice linear, positive linear relationships between estimated stiffness and stiffness rating. And what that means, in order, as Neville mentioned, in order to do that, I mean, it's fundamentally impossible to estimate stiffness without force information. So people are using some prior knowledge in order to do so. What is that prior knowledge from? Is it built from observing others move, or built from, or are we using our own neuromotor controller to do that? Those are still open questions. But as with most scientific experiments, we as humans, we can see these results, right? We can see human behavior, and then the hard part is how do we actually capture it mathematically? And one of the really exciting things was, I mean, our best subject in this experiment was a physical therapist. And when you think about it, that's what they're doing. I mean, the term muscle tone is a very elusive and controversial tone, but you can model it as an improperly tuned impedance. And what we see is that a physical therapist can very quickly pick up on whether somebody has, say, improper muscle tone or abnormal joint coordinations. So there may be some, again, this is for estimating from humans, right, or from typical normal motion, but there may be something that even just in the motion itself, we can extract information about the impedance, especially at the joint level. But I would also say, I mean, I've seen this several times in some work. I mean, the hard part is, right, you just have, is even just the very simple problem of like, F equals like K X minus X naught is like, that's an ill-posed optimization problem. I mean, right? Like, and so I think that's also part of the challenge that we all struggle with is, it's one thing to determine what are the values, right? What are the gains? But then how do you choose, say, an underlying trajectory or desired trajectory? And what's the trade-off between those two?
If I may, I would like to stress a relationship between two topics that we have been discussing. One is this rest length and the role of x0, x0 that we have just seen in this simple equation, which is at the core. And the other is the difficulty of measuring human stiffness or impedance. It seems to be different. But if you think a minute, we can probably easily measure the position x of a human arm and the force F. What we really don't know how to measure is x0, is where the arm should be or would be. That is really the point. Where is the reference point? That is what we don't know. And so there is this connection between the definition of the difficulties we have, I think. Etienne did that, of course, with taking many times a trajectory and assuming that once he used to perturbation, then the reference could be the average of the previous of the priors, but that was only doable in some conditions.
I know there's a few people working on this problem. Anyone want to step in? Have any comments?
So maybe I'll jump in. I think this is actually exactly what my poster is about today, is the do humans care about the rest length, or what in human motor control we talk about is the zero force trajectory. And I think we see evidence that they may, and that's ongoing work. But I think that it, just like Professor Rouse was talking about, if you change the rest length, or you don't know the rest length, you can generate almost nearly arbitrary time varying impedance looking behavior if you're only looking at the force. So I think it's a particularly important topic.
Just a quick thing. So we talked about nonlinearities when it comes to the stiffness and the damping. So that would also hold for your reference trajectory. So kind of going back to what Dr. Hubbard said, yeah, it's going to be an ill-posed problem. You're going to get, if you're doing it in a numerical estimation, you're going to get several suboptimal values, and you're probably going to have to pick and choose which one you're going to go with. I struggled with this problem several times because we tried to numerically estimate it, because building a perturbing robot is difficult. Dr. Rouse is talking about an exoskeleton just for measuring knee stiffness. And even if you have an exoskeleton, you still have to isolate the perturbation just to that joint. So I think forwarding these numerical estimation techniques is very important until mechanical or robotic technology catches up to where we have nice perturbing robots.
Yeah, and I mean, I think that also just brings up the point that Neville made earlier, is that the hard thing is once you start perturbing the human, they may change their behavior, right? And I think that's the thing. Like, to me, that's the real challenge, is that it's really hard to measure that exact phenomenon that you're looking at, and how do you counteract or account for that? And I think that's we don't know.
And it would also change based on what kind of patient you're dealing with, because stroke patients tend to have very different inherent stiffnesses compared to a healthy human.
Exactly. I mean, everything from that, and then also sensing right when I mean, that's something that's often overlooked in the motor control community, is that the sensing differences with patients may be different, and then you can affect that might also affect how they may be able to modulate their impedance or not.
So I have a very naive question for the motor control communities. How much is modeling a way to get around that, in the sense that if you could model the dynamics of a system and find a way to compute a variable impedance that kind of makes sense, or test different hypotheses of why would you have variable impedance, you can start maybe testing hypotheses that you could actually then see whether or not it plays out in people. Is it something that makes sense, or is not? Is there a value in that, or not, from your point of view?
So I think one of the, so yeah, I think there is a lot of value. And a lot of people have looked at models of limbs to try to get a sense for how impedance can help in different tasks. One of the challenges, though, in terms of a general computational solution, is we can't even model the impedance of a muscle very well. Again, we can do it really well for these small perturbations, but as soon as you get into dynamic conditions, there is no model that I know of that does a good job of estimating the impedance of even a single muscle. Now, once you start to think about whole limbs, I guess I can argue on both sides of the coin here, but in some cases, it can get a little easier, because in the case, again, where tendons become the dominant factor, they're much easier to model than muscles. So there are some instances where I think computational models, for example, at the ankle, will work very well. But for other joints like the shoulder, I think they'll work much less well, where the tendons aren't as big. So it's a good question and a great goal. And it's very useful in terms of trying to get at Ludo's question as to what is the role of impedance, or can it play a beneficial role? But it gets back to, I think, where we started the symposium, is what we really need are good measurements.
So I'd like to add on top of Eric's comment, just looking at muscle, for example, we're not even guaranteed that the functions are continuous. There's evidence that the velocity dependence of muscle force is discontinuous around zero. But step a couple of layers back, we had no knowledge whatsoever of what's going on in the spinal cord. There's a whole swath of interneurons that are coupling different muscle groups. There's a whole bunch of stuff going on in the cerebellum that we don't know much about. There's a whole bunch of stuff going on in the cortex that we don't know much about. So at the level of mechanics, we can model reasonably, but when you get to the complete control problem, I don't think we have it. So it's not that models are of no value, but you've got to be realistic about what we can, what we can measure and what we can guess at.
Then with all that complexity, our simple second order model works remarkably well for many conditions, right? But you need to remember that that's a model. So when you start to think about what is X naught, it gets back to this really complicated system. And I'd argue there's probably not an X naught per se in the nervous system. That it's our representation that works really well for certain conditions, but we need to understand the limits of that representation.